Okay, I've been asked to do a problem like this. It's an equilibrium problem, and that is the steam reforming of methane produces synthesis gas. So I have here water and methane, so water and methane, and produces synthesis gas, which is a mixture of carbon monoxide and hydrogen gas. And it says a chemist studying this reaction fills a certain flask with 3 atmospheres of methane, 1.7 atmospheres of water vapor. And it says when the mixture has come to an equilibrium, then we measure hydrogen gas to be 4.1. Okay, so how I would start this off is I would write down the chemistry that's going on. And so the chemistry that is going on here is going to be CH4 plus the water, this is all in gas form, is coming to some sort of equilibrium here with carbon monoxide and with hydrogen. Okay, always make sure that we balance that. Let's inspect that. I've got 6 hydrogens. Let's put a 3 right there. Okay, so this is balanced, I feel, and it is. So the next thing I like to do is write the equilibrium equation. So the equilibrium expression at pressure, using pressure, is going to be equal to the pressure of CO times the pressure of H2, which is going to be cubed because of that stoichiometry coefficient right there. And this is going to be divided by the pressure of the CH4 times the pressure of the H2O in that flask. Okay, so I have the chemistry, I have the equilibrium equation right here. Okay, so there's some nice things here. We can build ourselves an ice table that will be helpful to us. So we have initial change and then an equilibrium concentration. And this is going to be, I put my reactants first, CH4, move over a little bit, H2O, move over a little bit, put CO, and finally move over a little bit, H2. So here is my ice table. And so it gives us the initial pressures, and the initial pressure of the CH4 is going to be 3.0 atmospheres. For the water, it's going to be 1.7. Okay, and I start out with 0 of each of these right at the beginning. Well, the nice thing about this problem is it does tell us what the equilibrium pressure is of the H2. And that's going to be 4.1 atmospheres. That's at equilibrium. So I've got this part down. Okay, now I just have to worry about stoichiometry. Well, we know that it's assign the H2, since that's what it gives me, as our X value. Well, based upon the stoichiometry, I can take the coefficient in front of each of these. In this case, it's a 1 in front of each of these, but it won't always be the case for other problems. And I can divide that by that 3 right there. So the change here in the CO is we're going to add 1/3 X based on the stoichiometry. And the change here is going to be 1.7 minus a 1/3 X. And over here the change is going to be 3.0 minus a 1/3 X. Okay, or the change is just going to be a 1/3 X. Let me just get rid of those. Okay, so in the end our equilibrium pressures are going to be 3.0 minus a 1/3 X. Here we're going to be 1.7 minus a 1/3 X. And finally for our CO it's going to be 1/3 X. So here's our equilibrium concentrations in terms of X. Well, we know what X is. To go from 0 to 4.1, X has to be equal to 4.1. So what I can do after that, after I've set up a correct ice table, is I can just take 4.1 and plug it in for x to each one of these, and it will give me my equilibrium pressures for each one of those reactants and products. And I can just put that in now to my equilibrium expression that I've made here. Okay, so when I did it, so we already know that this is going to be 4.1. Over here, when I did it, I got 1.36667, carry a few extra there. And then for the CO, I got 0.3333. And finally, for the methane, the CH4, I got 1.63333. Okay, now I can put these into my equilibrium expression over here. So I have Kp equals the partial pressure CO, which I calculated to be right here, 1.36667. It's going to be 1.36667 times 4.1, but that 4.1 has to be cubed. Okay, divided by 1.6333, that's my pressure of methane at equilibrium. And finally, that's going to be times the water at equilibrium, which is 0.3333. So when you do that, you'll get something like 173.00, some other decimal places right there. But it's asking for this for 2 sig figs. And so for 2 sig figs, then, it would be 170 as my equilibrium constant here. If I want to put that into scientific notation, 1.7 times 10 to the second. Either of those should work. I think Alex prefers the bottom one right here. Okay, so how do I tackle this? I write the chemistry. Okay, the first thing I do is I write the chemistry. Then secondly, I write the equilibrium constant, the equilibrium equation. I make my ice tables, and I use the stoichiometry to get me those changes. Okay, and that's important to know. And then I get my equilibrium concentrations because I know what X is, and in all of these you'll know what X is. It's just building your ice table correctly. And remember, X is given to us because it tells us the equilibrium partial pressure of hydrogen is 4.1. It's giving us that information, so we just plug that in and do the algebra. So that should be able to get you through these types of problems. This was a little more complex because we have fractions, but you should be able to do these with no problem.